Sí, ya fui. No la escuchaste.
No, es que yo no estaba aquí, acabamos de llegar. Vengo
No, ya la pasé.
5 minutos. Let's give them 5 minutes, you know.
Okay, yeah, that's good. I like that. Yeah, the coffee.
It's not good.
They're not good, but it's
We
okay.
will try later.
Mm.
You want some water?
Is there water? That would be very good. Yeah.
No.
Okay. Yeah, thanks, Barbara. Don't. Okay.
Adelante, caminantes.
No worries. Okay. That's quite a lot of talks. So 3 talks. Lots of dedication. Yeah, it's tough for everyone to. It's 3 talks. I'll be exhausted. You're already exhausted. I should have a good sleep. But tonight we have to. Tonight we are going for the banquet. That's a good. Yeah. Yeah, you deserve for it. Yeah, I think that's. Maybe. Yeah. Unless Francesca is just over there. Yeah. No, okay. Justin.
He wishes. I'm sorry.
Yeah, I wish.
No,
Yeah. I should steal his ticket. Oh, no, it's all.
I'm Justin Reed, no, you show up at it. Of course, I'm Justin.
It looks like.
Okay. Sí. Bueno. Hola, queridos. Es un enorme placer para mí presentarles al doctor Daisuke Kawata. Les voy a decir muy brevemente porque dicen que hago mucho rollo antes de presentar a alguien, no los dejo hablar rápido. Estamos en una reunión, como ya saben, de GAI aquí en la sala Ignacio Chávez y hubiéramos querido que todos se expusieran, pero yo creo que no iban a aguantar todos. Somos varios, ¿no? Son varios los que podían. Entonces, lo hicimos así como en volado y entonces escogimos. Al final de cuentas, digo, todos son excelentes en lo que hacen. Entonces les voy a platicar del doctor Kawata. Él es originario de Japón, realizó sus estudios de doctorado en la Universidad de Japón, Tohoku. It's good. Su tesis es a Numerical Study of the Formation of Elliptical Galaxies. Tiene aproximadamente 80 artículos, cerca de 2.500 citas a estos artículos. Es muy joven. Uno nunca sabe en los japoneses, ¿no? ¿Qué tan? Pero él es muy joven. No envejecen, simplemente. Sus temas de… Sí, ¿es porque comen gato? ¿No eran los chinos? No, pero sus temas de experiencia
Okay,
son…
What
is she saying?
No entiendo.
I'll explain you later. Sus temas de expertise, no sé cómo de expertise, son formación y evolución de galaxias, arqueología galáctica y simulaciones numéricas. Entonces nos va a hablar de lo último que tiene en este momento. Thank you very much.
Okay. Thank you, Barbara, for completely unknown introduction, but sounds very good. And thank you very much for coming for this series of 3 talks we are providing. And thank you very much for your time, for coming for my talk too. I will present my recent studies with these my collaborators. But first of all, whenever I give a talk at abroad, I always take opportunity to introduce where I'm from. So I'm from a Mullard Space Science Laboratory called MSSL, University College London, and I'm not sure how many people even know the University College London, so I will start from introducing our university. So we call it University College London, UCL. It's a quite old university, and some of you may know, but this is the first university in England for students of any race, class, or religion. So there was Cambridge and Oxford, but there's only a few limited people could go into the university. So UCL is first university open to the everyone, and also the first university for the female student as well. And it's based on London, so if you come to the British Museum, then you can also visit the UCL and just see where we are. And there's a good number of Nobel Prize winners, and we are rated as a top university in the UK national-wide research excellence framework as well. And we can always find some very good measure of the university, and I'm already showing this ranking in this year, and we got a fifth in the international world ranking university, and I'm not going to tell you where we are in this year, but we got it, so I will show you this. So UCL is in London, and MSSL is far away from London, and this very green area. I can also show you that where the Justin Reed, my dear friends, also work in Surrey, so they are here too. So we are closer to Surrey than the UCL. But this is a very nice green area, and this is our place, and you can see that there is no other house, not many other houses than the green, and there are lots of cows and etc. So it's a very beautiful area, and this is the top of the hill, and this is our house. And in fact, why I'm showing this is Guinness family used to live in this very nice English manor house. So. And also in a sunny day, which is very rare, but you can see the very nice view of the countryside in the UK. So if you come close to the London area, just let me know. We will invite you here and also invite you to the nice countryside pub in the UK as well. So MSSL is a space science laboratory, and this is the largest university space science lab in the UK, and we have about 160 people working there. And we have engineers and scientists work together and making a contribution to the space science missions. And we work with a lot of international partners, and also our research group is quite diverse, but it's connected under the theme of the space science mission. And I'm of course in part of the astrophysics group, but the MSSL itself also currently contributing to the many projects listed here. And in the future, we will also working, our engineers and scientists working for these quite exciting projects, including James Webb and Euclid and Plato, which is quite related, also Athena, quite related to the astronomy. Okay, and I'm here for the Gaia working workshop. And MSSL is also contributing to this RVS, radial velocity spectrograph, and also spectroscopic data processing team. And so our passion is with this Gaia mission. And I'm always interested in the Milky Way science and how the galactic, especially how the galactic disk is formed. And today I will talk about the impact of the flaring disk and the radial mixing on the galactic thick and thin disks. Okay, so this is the outline I will talk about. The first, I will define that, give you a sort of a definition in this talk of thick and thin disk, and I will talk about this quite old paper, but which we published in 2004, which is showing a thick and thin disk formation scenario I still love. So I will talk about that, and also some recent development based on this scenario. And also I will talk about this impact of radial migration and the flaring disk on, especially on the thin disk chemical distribution. Okay, so let's start from the definition of the thick disk and the thin disk. And back in 2083, Gilmore and Reid looked at using observational data, calculated the number density of stars as a function of the galactic height. So that if we are here, and they look at the number density as a function of the height. And they got this profile, and if they interpret that, there's a nice exponentially falling disk here, which they call thin disk, but there's another component here, and they call thick disk. And so Milky Way has this thick and thin disk population, and it's now we know that almost all, I think it's all disk galaxies has a thick disk. And so thick disk is ubiquitous. So if we study the thick disk in the Milky Way, we hope we can understand the thick and thin disks of the other disk galaxy as well. But anyway, so this is I call this is geometrically thick disk, so that the number density enhancement in the high galactic height. So I call that as a geometrically defined thick disk. But you can also so this is the two components in a disk, but there's another way of defining these two components. And that's came from chemical abundance analysis. And this is, I'm showing this paper from Farman 2011. This is showing x-axis FeO/H, iron abundance, and this is the ratio of the magnesium and the iron abundance. So this is how metal rich the star is, and this is magnesium is mainly coming from type 2 supernovae, whose lifetime is much shorter, and iron is mainly coming from type 1a supernovae, and their lifetime is much longer. So these are stars, the mg/Fe or alpha/Fe we call, sometimes it's high. These stars are more enriched by the type 2 supernovae. And then type 1a kicked in, these stars probably formed after these stars, and have a lower mg/Fe. So this is a nice diagram for galactic astronomer use to interpret the characteristics of the stars. And this is paper clearly show that there's a nice thick disk stars, and there's some gap. Just ignore this. And then there's another sequence we call the thick disk population. So in this chemistry diagram, we can also define this thick disk population, which may form early epoch before type 1a supernovae kicked in, and this thin disk population, which is another population. So there's another dichotomy in the galactic disk defined in the chemical composition. So this is, I call this as a chemically decomposed thick and thin disk population. Okay, so there are two definitions of the thick disk and the thin disk. So of course, we want to know that are they related to each other or completely different? And there's a very nice series of papers by Thomas Bensby and his collaborator. And this is showing a 2014 paper, some sort of summary paper. So they had a very detailed abundance measurement for the solar neighborhood stars. And they plotted, okay, let's start from this bottom panel. And their orbital characteristics, or velocity characteristics. This is the rotation velocity. This is the sort of mean of the radial and vertical velocity. So these stars, not much vertical or radial velocity is there. So it's a very cold population, but there's a rotation, very nicely rotating stars. So that they call that as a thin disk stars. And these kinematically hotter stars, they call the thick disk stars. So this is a sort of this is kinematically defined, but these stars are the candidate, or these stars should be. This is how now in the solar neighborhood, but in some time, because they have a vertical velocities, and they should end up some point and a higher disk height as well. So this is the same definition as basically geometrically thick and thin disk. So once you have done that, you can put in this chemistry diagram again, and this time is using a titanium abundance, but just think about same as a iron abundance, how metal rich they are, and this is a bit flipped from last slide, but it's iron abundance divided by the titanium abundance. So titanium is also mainly coming from type 2 supernovae, so these stars are mainly produced, enriched by the type 2 supernovae. Okay, so this geometrically thin disk first, these population, if we plot that, they are mainly the they are mainly in this thin disk population, but there are lots of high alpha over here or low Fe over alpha thick disk population too, if you look at these two chemical compositions. And it's a geometrically thick disk. There's another low alpha over Fe stars or high alpha Fe over alpha stars. So basically, the thick disk definition of the geometrically thick disk and geometrically thin disk has a quite a big overlap, and they are not the same as a definition if you divided stars as a chemical composition by the thick disk population and the thin disk population. Okay, so even if thick disk this geometrical thick disk, there's a thin disk population, so there's some overlap going on. And these are symbols showing this. They have also age information as well. And these blue are the young stars, and these red circle are older stars. So if you look at that, and then it's this thick disk population mainly dominated by these older stars, and the thin disk population is mainly dominated by the young stars. So there's some quite good correlation with this younger thick disk, old thick disk, and also young age of younger stars are also populated in a young thin disk population. So it seems like, and also I think this is the sort of consensus in the current point of view of the defining a thick disk and thin disk. It would make more sense to define the thick disk and thin disk population using this chemistry diagram. So I will mainly use this decomposition of the thick and thin disk using this chemical abundance diagram. Okay, so geometrically thick disk is not the same as a kinematically defined thick disk. Okay, so this is a solar neighborhood study, but it's now this is a beautiful survey by Sloan Digital Sky, part of Sloan Digital Sky survey, but this in the STSS3, there's a survey called Apogee survey, which is a near-infrared high-resolution multi-object spectrograph survey. And this is the footprint of their observation, their survey. But they use the near-infrared, so the dust extinction in near-infrared is much lower, so they can go very low galactic longitude. So this is the galactic plane. They have a sampling quite a lot of thin disk and thick disk stars, despite very high dust extinction in optical, but they use a near-infrared high-resolution spectrograph. So this, and now that they are doing an STSS4, there's Apogee 2 survey. They are filling this southern part as well using Las Campanas DuPont telescope. So there will be quite exciting data will be coming for the southern hemisphere too. And then this is a beautiful paper by Hayden et al. In 2015 using Apogee data, and they're plotting all the giants alpha by Fe versus Fe by H. And we are looking at Thomas Bensby's work was around the solar neighborhood, so we are looking at this kind of thing, and there's a thick disk and thin disk population. But they are looking at a different radius and different vertical height up to 2 kiloparsec, and you always see that there's a nice thick disk sequence given a high vertical height, and there's a thin disk population. So this sort of dichotomy in the chemical composition working very well in a very large region of the disk. So this is another example of this defining a thick and thin disk by a chemistry will be useful. Okay, so let's go to the second topic of the this Brook et al. 2004 thick disk and thin disk formation scenario. And this is one of the thick disk and thin disk formation scenario we proposed in 2004. And there's another candidate of the second syndisk formation scenario and listed here, but I'm not going to talk about this because my heart is here. So this is a very biased talk because you are listening my talk, and I will talk about this. And of course, I'm very interested in discussing about these other topics. So if you're interested, just talk to me later. Okay, so back in 2004, so what we have seen or what we have found from numerical simulation we learned in around early 2000, and we plotted this is the stellar density map at the redshift 1.4 to 1.0. This is a snapshot, and this is the edge-on stellar disk is forming in here, the very high redshift, and this is the gas edge-on density image. And you can see that there are lots of small galaxy is merging into this central disk. So they are bombarding those central disks. And if you look at this gas disk, which should be forming stars, and their disk is quite disturbed. So their stars forming this time is much thicker, so dynamically very hot. So we are saying that this is the time when the thick disk star is forming. Because of this hierarchical clustering, predict many multiple merger at this epoch. Okay. And so in observation, so that was 2004, but in later 2000, there's a duality, for example, IFU spectra can really look at the kinematics at the disk-like galaxy at the quite high redshift. And they look at this 2D velocity field and fit the rotation velocity and the particle velocity dispersion. And what they got in this rotation velocity versus velocity dispersion, they're showing quite a low value. So it means velocity dispersion is more dominated. We think because it's a lot of multiple merger is going on. And then it's comparing with this local disk. Is usually rotation is much more dominant than the velocity dispersion. So the local disk is much higher, V over sigma. So this is very different. So this time it's probably, I'm saying, to be corresponding to the thick disk formation time. And back in 2004, we have looked at the snapshot at redshift 0. And this is the snapshot and face-on stars and gas, edge of the stars and the gas. And then we can define the sort of solar annulus at around 80 kiloparsec and pick up these star particles and look at the properties of a star particle within around 80 kiloparsec. And then if you look at that, and then we know the age of the stars when they're born from our simulation. And you can also calculate the velocity dispersion at redshift 0. And then you can see that in older stars having a high velocity dispersion because they formed when the lots of merger is going on. And then also we have a chemical evolution is included in our simulation. And when we look at this alpha over phi versus F over h again, then we had some nice two populations we could see. And these stars had a higher alpha over phi because they formed much early epoch. So we could also reproduce this dichotomy in the chemistry diagram. Okay, and this is still, this was consistent with our observation available in 2004, and this is still consistent with the recent observations. This is the sort of a compilation work by Haywood et al. 2013, and showing the age versus velocity, particle velocity, and this is the velocity dispersion is increasing for the older stars. And this is again alpha by phi by phi by h, and you see that these two different nice two populations in a solar neighborhood. So it's this scenario, I still love it, and because I think it's still promising, surviving scenario. So we want to explore this Brook et al. 2004 scenario further. Okay, and this is a bit of a fun work by the Chris has done. And so this is our simulation snapshot of our simulation done in 2004, 5, and 6. And this is the redshift in x-axis. These are simulations, and this is our old simulation, and this is the face-on, edge-on. And this is the Stinson et al. 2013, so more recent, higher resolution simulation, and also Chris's 2012 simulation. And it's basically qualitatively very similar evolution. So the earlier disks are smaller and thicker, and then getting thinner and building up thin disk. And this is a snapshot from the Fandokam et al. 2013. This is the observation. I think it's from the HST snapshots. And you can see that it's a much higher. In the ballpark sense, these high redshift galaxies are much thicker and smaller compared to the nice local disk galaxies. So in a qualitative sense, we are very happy to see that our simulation in a very old one is still consistent with recent simulations and also consistent with high redshift galaxies, nature of the high redshift galaxies. Okay, again, the Hayden et al. 2015, and going back to here, we predicted that in 2006 we should have a smaller, thicker disk because thick disk forms first, and then thin disk starts building up. So thin disk should be bigger than the thick disk. And so if you look at this apogee data with a bit of biased eye, and this is the radius of the 11 kiloparsec. And if you look at further than radius of the 11 kiloparsec, this is a thick disk sequence, which is very clear in the inner disk, but there's not much thick disk population in the outer region. So it seems like, but the thin disk is still there. So a thick disk seems quite small compared to the thin disk, if you define that in a chemistry diagram like this. So this seems still consistent as well. And there's another observation in the Milky Way, and claiming that the thick disk is bigger than thin disk. So what they have done is using SSS photometric data, and counted the number density of the stars in the different vertical height and radius. And you see that the thick disk population and the thin disk population. And what they concluded is the scale length of the thick disk is bigger than the scale length of the thin disk. But I said this is a geometrically defined thick disk. So this is not chemically decomposed thick disk. And what they have done is, ignoring this chemical composition, they define the thick disk as a D's population and thin disk as a D's population. So that's what they concluded. But this is so inconsistent. It may be inconsistent what I said. The thick disk should form earlier and smaller and thicker. And but there's one solution to that. And this is work what I have done with Awad Rahimi, my ex-student, and published in 2014 after we rejected by the 3 referees from the 3 journals. But I really like this one, and finally we published this in 2014. So the work was done in a much earlier time. And but what we said is, when we look at a snapshot of the cosmological simulation at redshift almost 0, and then we have divided this old thick disk population and young thin disk population, and plotted the radius versus vertical height. And what we found is there's a compact thick disk, like what we showed that in a Brook et al. 2006 paper. And then, but the thin disk is flaring. We call flaring because vertical height is increasing. Vertical scale height is increasing as a function of as increasing radius. So the thin disk is flaring. So if we look at, if you did number count of stars, then basically you define the geometrically thick disk is like this, under this area, and then thick disk is chemically defined, or old thick disk is contributing in the only inner region. And outer region, this thick, geometrically defined thick disk is contributed by the young flaring thin disk. So then you can get in a bigger scale length for the thick disk, a geometrically defined thick disk. And this is also quite interesting because thick disk stars formed earlier. So as I said, it should be higher alpha by phi and lower FU by h. But the thin disk stars should have higher FU by h and lower alpha by phi. So if you look at the metallicity gradient in a high vertical height sample, and then you should expect this trend. And quite interestingly, this is from apogee survey again by the Andres et al. In 2014. And what they have done is, this is the left-hand side panels, radius versus the metallicity at the different height. So if you look at the galactic disk plane, almost within the disk plane, they see that in what we expect is a negative metallicity gradient, higher metallicity in the inner region and lower metallicity in the outer region. But if you go up in this height, scale height, a high height, and then you have a positive metallicity gradient, which is consistent with what we had showed in the previous slide. And this is the alpha by phi gradient. So then in the galactic disk, it's completely flat. But if you go up the disk, and then there's a negative alpha by phi gradient, which is also consistent with what we predicted in the Rahimi paper. Okay, so again, this Hayden et al. One, I think this is the final one I show. And but again, if you look at this flaring disk idea, admittedly very biased view, I see that this thick disk population is truncated, as I said previously, and then thin disk population seems flaring because there is no much thin disk population in the inner region and high height. But there is a thin disk population in a high vertical height in the outer region. So it seems like this is flaring. And this is not only us, what we said, that the flaring could be quite important, especially in the outer region. Ivan Minchev did that and using different numerical simulations, but he divided not two populations, but it's these different lines showing a sample of different age stars, like a mono-age population. And he showed that the older disk is thicker, and then younger disk is also flaring as well. And if you summed up these two all population, he also look at the scale height of the younger disk, scale height of the geometrically defined thin disk versus geometrically defined thick disk, then it's constant. So if you look at, it is possible to make a larger geometrically defined thick disk, making a disk as a sort of composition of different old stars, different ages of the stars, but the younger star is larger and also flaring. And the flaring idea is not new, and this is a 2014 Nature paper saying Cepheids are variables, and they found that so we are here in the galactic center. They found the Cepheid, which is a very young population, and in high vertical height, and they're also talking about that. There may be some galactic disk. Young thin disk is having a flare. And also, even in 2087, in Scoville and Sanders, show that the CO disk, or molecular cloud disk, molecular disk, which is the gas which is forming stars, are having a flaring. And this is a more recent paper by Nakanishi and Software, and they show that the radius versus this height, and this is the galactic plane, and this is H1 and H2, and they show that this nice flaring. And this is a much more clear one, galactic distance versus the H2 molecular disk vertical height, and also H1, both are flaring as well. So it's a flaring, it's not very surprising thing to find. And okay, so the final topic, and this flaring, how this may be important for understanding the chemical distribution in a thin disk. And also I will talk about this new, important concept, especially in a thin disk, of the radial migration. Okay, series of the paper which we published with Rob Grant, my ex-student, now in Heidelberg. We looked at spiral arms forming in the N-body simulation and see how they look like. And this is a face-on view of the stars and gas, and edge-on view of the stars and gas. And this is my simulation using my N-body SPH code, and this is the resolution. But what I wanted to show you is that if you look at the one spiral arms in this animation, they keep disappearing. So the spiral arm seems that looks like a transient, but in each snapshot, there is a very nice spiral arms are forming. And also, another thing we said, also we found from this observation of the N-body simulation, the spiral arm is winding. And the spiral arm is, in fact, it's co-rotating with the stars. So it's like almost like a material arm. So they are rotating, spiralarms rotating faster in the inner region, but are rotating slower in the outer region, as the stars does. So the spiral arm is co-rotating in every radius. And if you look at the velocity field, this is the plotting this is the angle versus radius. So this is the radius, outer region, inner region. And then the spiral arms. Then the stars, for example, behind the spiral arms, they are getting a torque from the spiral arms and accelerated and increasing angular momentum, and they migrate outwards. But the spiral arm is co-rotating with stars in every radii, so they cannot pass the spiral arm. So they keep accelerated and have a very nice radial migration, we call, so going outward in the backside of the spiral arm. And the front side of the spiral arm, they feel the sort of torque from the spiral arm, so they lose angular momentum, and then they go inward. But when they move the inward, they still co-rotating with spiral arm, so this spiral arm cannot pass these particles or stars, so they keep migrating until this spiral arm disappears. So this is what we found in n-body simulations, and so the radial migration seems quite efficient in thin disk stars. So what this radial migration will do for the chemical composition in a thin disk, we now know that in a chemical distribution by the apogee data from the inner region of the disk versus outer region of the disk. So we can now compare the prediction from the n-body simulation with the real data. And but radial migration is basically mixing of stars in the radially. So if there is a nice metallistic gradient, if the radial migration is so efficient, you may expect it's completely flattened the metallistic gradient. So we can also look at that, comparing with n-body simulation. Okay, so first, the fact of the observation. And this is the Gaia ESO survey. It's done by the BLT telescope in Chile, in an 8-meter telescope, and the lots of effort done by the Gaia ESO survey team. And this is one publication by the Mikolaitis et al. In 2014. What they have done is, first they have looked at all the disk star sample in this abundance diagram, again alpha by Fe versus Fe over H. And then they divided this thick disk population and thin disk population. And here I said that radial migration is more efficient in thin disk stars, so I will focus on the thin disk stars. And this is a plot for the radial metallicity gradient. Radial metallicity gradient for the thin disk stars defined by chemistry. Okay, and there is a clear negative metallicity gradient, so the radial migration shouldn't be too efficient to flatten the Milky Way thin disk metallicity gradient. So there is a significant metallicity gradient. And this is a vertical metallicity gradient. And this is for the thin disk population. Again, there is a negative metallicity gradient. And this is these thin disk stars, and whose age is probably between 0 and 10 gigayear or 8 gigayear. But what's happened for the mono-age abundance, mono-age thin disk population? And this is very difficult to get the age of the stars, but now we have a nice data from Kepler. And Kepler is a planetary planet mission to find the planet system in the stars. But they are basically studying the one region of the sky for 5 years. So they have very nice light curve for the stars in that field. And you can use that light curve to understand the seismological motion of the stars. And then you can get the age or mass of the stars, and then you can get age of the stars. That's what I've done by the Luca Casagrande, my collaborator. And I asked Luca to plot that, pick up his sample of the stars with an age between 3 and 5 gigayear, and then plotting Fe over H versus vertical height, and see what is the vertical metallicity gradient is. And what he found is still using, even picking up this particular range of the age, still you see that negative vertical metallicity gradient, and roughly the minus 0.1 dex per kiloparsec. So so this is the observational fact, and I have done some simple numerical experiments setting up the initial condition of the disk following this Brook et al. Scenario. So I said in the Brook et al. Scenario, there's a thick disk population stars, a thick disk which is smaller and thicker, and then there's a larger thin disk stars. So this is the phase-on and edge-on. So this is the initial condition. And we put these disks in the dark matter halo potential, and then let them go. And then we run for the 8 giga-year, and then we see that in the thin disk stars, there's a bar developing, and it's very difficult to see, but there is some spiral arm is going also formed, and they are also correlating as what I showed in the previous slides. So there must be quite a lot of radial migration is going on. And this is thick disk population. Interestingly, you see some bar also in a thick disk population too, but that's not, we are not talking about this, but we will focus about this population. Okay, so this is the N-body simulation, which is not including like a chemical evolution or gas dynamics, but it's very simple numerical experiments. But we can tag the stars depending on, for example, radius, and then all the stars in the inner region, we can assume they are higher metallicity, and outer region, lower metallicity, assuming some nice metallicity gradient. So what I've done in the initial condition, I tag the stars in the inner region of the some metallicity and outer region the some metallicity, and look at what happened after the 8 giga-year. And for this example, I assume some nice metallicity gradient with a very small dispersion of the metallicity and no particle metallicity gradient. Because I assume this very small dispersion, because I expect that in the thin disk, molecular cloud, molecular gas is confined within a very small particle height in a disk, usually which is observed. And so it should be well mixed, and in a partically, chemical abundance should be well mixed in a partically. And also, if you look at the young B stars abundance, the work by this is not by them, but this is a review paper talking about this, but some nice measurement of the metallicity abundance of the young B stars, then compared to the thin disk dwarf stars, the metallicity dispersion is much, much smaller. So when they form at each radius, their metallicity distribution must be very small. So that's why I assume this very small metallicity distribution. And then what happened in about metallicity gradient, the function of radius at t equal to 8. Then there's a radial migration. So these very nice high metallicity stars move to the outerwards, and these outer disk stars maybe move to the innerwards. So basically, they have lots of mixing going on. So the metallicity distribution at each radius is going to much thick, wider. But still, this is a mean metallicity and dispersion, and there is a metallicity gradient even after this 8 giga-year of the lot of radial mixing. And sorry, this dotted line is initial assumed metallicity gradient. And this is sort of consistent with, again, this is the solar neighborhood metallicity distribution function of the Lugar-Sangrande's work in 2011. What they have done is young stars metallicity distribution, the metallicity versus the number of stars or fraction of the stars, is much, the distribution function is much thinner, but it's in the older stars, they are having a much wider metallicity distribution. And what they also said that is these young, lower metallicity stars may be coming from the outer region, and these high metallicity stars are maybe coming from the inner region. So this is a sort of one of the evidence of the radial migration is happening in the Milky Way. So using this same metallicity tagging, I have also calculated particle metallicity gradient, and I got some surprise. So this is a t equals 0. I said that I assume there is no particle metallicity gradient at the initial condition, but after 8 giga-year of having a lot of radial migration, I found a positive metallicity gradient, which I didn't expect. And then the reason why this is having a positive metallicity gradient is, for example, in the outer region of the disk, that this is the particle height versus the initial radius of the star are these particles. So, for example, this outer disk sample, outer disk particle sample at the rate t equal 80 gigayear, where they come from is mainly, especially in a high vertical height, they are coming from the inner region. So this is their 10 and 14 kiloparsec region, but if they are coming, these particles arrived in this outer region, but coming from the much more inner region. And this is easier to understand if we plot an initial particle energy, and this is a different radial region of the sample, and if you look at the high vertical height sample, they are having, initially they had high vertical energy. So they were in the inside of the disk and having a high vertical height, but the inner region of the disk, they have a much dense thin disk. So their vertical motion is maybe not very large, but when you move them to the outer region, keeping a particle energy, then in the outer region they have much more larger amplitude of the oscillation, because in the outer region the disk surface density is much smaller, so you can have a higher particle oscillation and end it up to the higher particle height. So that is making a positive vertical metallicity gradient after the radial migration. And yes, in fact, it's a higher energy, vertical energy distribution in t equals 0. Okay, so I show that in Lugar Casagrande's data. If you look at the mono-age population, there is a nice vertical metallicity gradient. So if radial migration brings a positive metallicity gradient, so radial migration should be long and shouldn't be happening. So, so I'm puzzled by that. And one of the solutions I came up with was putting, again, the flaring. So we assume the stars formed in a flaring disk, like what we see in the molecular cloud distribution. So we put on this thick disk, like what we have done in the previous simulation, and another population, the thin disk. And then I put on this flaring disk, second thin disk, and assuming this is formed 8 gigayear ago, and then evolved to the redshift 0, which is 8 gigayear later. And then this flaring disk is also suffered from the radial migration, and but still having some flaring geometry as well. And so we will look at the metallicity distribution after this 8 gigayear of this flaring disk. So again, so we concentrate on this flaring disk. We ignore this population, and then we tag the metallicity, again putting the same metallicity gradient as what we have done in the previous simulation, and nice very thin metallicity gradient. And then what happened? And this is the vertical metallicity gradient again, and this is the inner region, and this is the 10 kiloparsec. Sorry, I don't know how it happened. And this is the outer region, and this is the redshift at t equals 0 initial condition, and it's almost flat. But then after the 8 gigayear of the radial mixing, we get the negative metallicity gradient, because we have, this is the energy distribution of versus radius in the initial condition. We have much flatter energy distribution. So again, looking at, let's say, the inner region of the disk, and that these high vertical height is mainly coming from outer region of the disk, and which has the higher vertical height. So it's a flaring disk, and going flaring in outer region, and it's but an 8 gigayear later of the radial mixing, but a high vertical height is mainly distributed by the stars, which was in this flared outer region. That's very easy to, I guess, easy to imagine. So basically, all the high vertical height stars are populated by the stars in the outer region. So we can look at the metal distribution function in the disk plane versus the high vertical height. And this is what we have done, what we have we see. And this is the metal distribution function in the inner region, middle of the disk and outer region, and this is the high vertical height. And then in the outer region, the MDF is not changing too much, but in the inner region, they are populated in disk from the outer region, so they have more skewed metal distribution function at high vertical height, which is sort of consistent with this apogee data again. And this is the metal distribution function in a different vertical height. And if you look at the inner region of the MDF, and then within the disk plane, they are quite high metallicity, but above the plane, they are more dominated by the low metallicity stars. Okay, so this is what I wanted to say. And so flaring disk seems quite interesting thing. And so we really need the structure of the disk, which maybe Gaia give us, and also the metallicity. So vertical metallicity gradient could be very interesting measure for the radial migration. And also maybe flaring also tells us by the chemically decomposing thick and thin disk. But what we need also additional information of looking at this mono-age population. Maybe this may be coming from the, can come from the astroseismology, and this astroseismology data is now came from the Kepler, and now the Kepler extension of the K2 is looking at the different direction of the galaxies. And also what could be more even exciting one is the Plato, which will come. This is the ESA's next medium mission. This is will be launched in 2024. This is again the planetary mission, but they cover using this many number of camera, and they cover a large area of the Milky Way sky, and this will provide us the bright stars astroseismology data, which means the large region of the sky we can have the age information. But this time we have a Gaia data, so we can see the structure of the mono-age abundance, mono-age populations. So this is what I wanted to say. Thank you very much for listening.
Thanks for your talk. I'm wondering, what are the mechanisms to produce the disk flaring? What do you see in the simulations? Probably this you could comment something about that.
Yes. Let's say first, I think it's in this level of flaring. What we have done in this numerical experiment, which is not too much. And we can see that even in isolated disk galaxies simulations, like what we showed in this kind of simulation. And this is very difficult to see. This is the older simulation, and we have much higher resolution simulation. And because of the feedback, these outer region of the disk is heated vertically and more compared to the inner region. And because of the disk is much more dense in the inner region, the outer region is much lower, so that basically this feedback can also making a flaring disk. So if I plot the cold disk in this RZ plane, like I showed, I also got the very similar flaring pattern. So the feedback, supernovae feedback alone can also bring this kind of flaring molecular cloud distribution.
Are there some observations, I think, about the velocity dispersions, the gas velocity dispersions in the others? So they are higher, yeah, probably because, as you say.
No, it's in fact in the velocity dispersion is higher in the inner region, and it's going lower.
The vertical ones.
Yeah, although it's almost constant, but it's it's the same vertical velocity dispersion, but this is let's say the vertical stirring force is lower. So if the velocity dispersion is flat, then geometrically the gas can be getting thicker. Yes, so velocity dispersion is a very good point, and but this is not velocity dispersion itself. Not tells you how thick the gas is. It depends on what is the potential in the vertical direction. So and this, when I look at this just isolated galaxy simulation, I also see that in a cold gas is flaring. That's what I got the idea as well. But it's, another thing is perhaps in the Milky Way we have lots of satellites going around like Sagittarius stars, so that can bring another factor of the flaring too.
Thank you. Daisuke, do you think that radial migration would increase sizably the age spread of the thick disk, which would be a doesn't have a very well, it's not entirely clear, but we think that the thick disk doesn't have a very large age spread.
Yeah, so so this is thin disk, and thin disk, if you look at the age metallicity relation in the solar neighborhood, we have huge scatter with the same age, same metallicity. So that is also the evidence of the radial migration. But it's going back to your questions, the thick disk, and yes, of course, the thick disk is maybe between the, let's say, the 8 and 10 gigayear, or maybe 9 and 11 gigayear, let's say, or like a 2 gigayear population. But they are much more high velocity dispersion supported system, like this. It's showing like this. And what we think, and also what we see in apogee data, the thick disk population has no metallicity gradient, radial metallicity gradient. So the metallicity is radially mixed very well. But this is, I think it's easy to understand because it's if the thick disk is formed in early epoch when it's lots of merger is going on, their velocity dispersion is very high, and also the gas velocity dispersion is also high, so the radial mixing must be quite efficient. So what we think is basically thick disk is formed having a very flat metallicity gradient. So yes, so going back to your question of age, and the age would be quite interesting one. And but if it is a metallicity gradient, and then the flat metallicity gradient is only thing we know. I think it's the age for the thick disk stars. It's very difficult to tell. So
yeah, that's part of the problem, because people are not entirely sure if there's the 8 to 10 gigayear population in the thick disk, or if it's just old, between 10 and 12 or something like that.
But it's interesting tentative evidence. It's analyzed by the Annie Loban, and she looked at that color marker diagram of the inner region of the disk, and what she claimed was thick disk. It's older thick disk. It's thicker and bigger, and then thick disk getting thinner and also getting smaller. So that's a sort of photometric analysis by her, and which could be very interesting because in a thick disk, vertical metallicity gradient is negative, although radial metallicity gradient is flat. So what I'm guessing is perhaps the thick disk, older thick disk stars, chemically radially very well mixed, but it's thicker in the older one, but it's gradually getting colder and colder. And then you can create a vertical metallicity, negative metallicity gradient because younger thick disk is thinner and also more metal rich. So you can explain the negative metallicity gradient. And if or not, younger thick disk is smaller or bigger, it could be quite interesting questions. And I think we need more data to really prove that.
And the other quick question was, what's the time scale for radial migration to start being important? And do you think that if you look at tracers of different ages, as these mono-age populations that you mentioned, if you think you can maybe look at a very young tracer in disk and not yet see the evidence of radial migration, but then when you take an older one, then maybe you...
Yes, so if you do this kind of thing in a different radius, that could be a perfect thing to do, right? And then if this is a older population, it's created by the radially migrated outer region of the stars versus stars coming from the inner region.
So the time scale is of gigayears?
Yeah, I think it's there's another studies by the Haywood 2008. It's the gigayear between 1 gigayear and 2 gigayear. Then this metallicity distribution function is almost getting similar. So within the 2 gigayear, this very sharp metallicity gradient can be more blurred by the radial migration. So it's quite fast. And I have done the same exercise of this with this between 5 gigayear and 8 gigayear, and still you can get a positive metallicity gradient. So radial migration is already changed the metallicity distribution even within the 3 gigayear.
Thanks.
Okay, one last quick question and quick answer, please, because there's another activity
Yeah,
at one.
sorry, yes.
Okay, I have some concerns about the strength of the radial migration that you predict with your models. If you compare with the extragalactic results, we have a much narrower dispersion in the abundance gradient that is basically tracing the thin disk. And indeed, we never find something bigger than, well, we define some kind of a parameter like it's a maximum radial mixing. It's in the maximum value in different articles is of the order of 0.3 defective radii. If you translate to the Milky Way, that's about 1.5 to 2 kiloparsecs. From the plots I have seen, it looks like this is a much lower in your simulation. That's that plot.
Yeah.
The radial mixing here will be huge. If we had that radial mixing, we should see this kind of gradients in galaxies like our galaxies, and we don't see that. So it's much narrower than that. That's one first point. The second point is that you basically predict that with time, the abundance gradients should get flatter. And most of the results we have get when we decompose the stellar populations for extragalactic sources, we find exactly the contrary. So the abundance is I mean, that's not what we see. I mean, the younger stellar population have a flatter, but the older is steeper. Yep. So if it's the oldest, the one that have more time to migrate, this should be the opposite. So how we reconcile these two things? Because, and by the way, the slope seems a bit too much for me. I mean, if you compare also with galaxies like Milky Way, the abundance gradient we used to show is more shallower than that. Yeah. So how that match?
This is a quite very good point, and I cannot answer this. But the reason why I cannot answer is we don't know the initial metallicity gradient. So this could be very interesting to compare with high redshift metallicity gradient. And so if you look at the local disk metallicity gradient, it can be anywhere, depends on the initial condition. So that's why I assume the steeper one you spotted very well.
But not the dispersion. So the dispersion is huge.
Yeah, dispersion is difficult in the external galaxies, right? And also this looks like huge, but if you look at the MDF, it's not too bad. And I show the MDF profile in the final slide of my talk, but it's not too bad. And but this is a very important point, and this is one numerical experiment, and this may be overestimating radial migration, but if we did similar things with the different strengths of spiralams, of bar, and etc., and then we can also constrain how the disk bar stronger was in a very high redshift or early epoch.
Let's talk later, because we have huge amount of data that I think will help in this simulation.
That's my aim. So we've done lots of things and finally fit the data, and then we can find that what kind of strengths of the radial migration should be.
Ensenada, do you have any question? Ensenada?
At all.
Let's assume. Okay, so.
Are they going back? Thank you. I think it must be here. Thank you.
Well, I don't think so.
Yeah, it seems like it's turning off.
Okay, well, let's thank the speaker again.
Yeah, thank you. Yeah, sorry.
Yeah, sorry, but there's an exam right now.
So. Really? What time?